Welcome to lecture 16. Today we'll be covering the structural failure criteria for metals. And in this class, we've already covered a number of topics um, in which these criteria will be needed to satisfy those requirements. As you remember, we covered the launch vehicle standards. We'll still need to cover the FAR regulations later for aircraft, and that's coming up. But for now, what you want to do is pause it for a little bit, learn about the structural failure criteria that's used for metals. I won't go for the I won't go into the failure criteria for composites. That's covered in the composites course, which you can actually look at. But for now, I have actually invited Dr. Nicholas Nordendale, who has extensive experience in failure mechanisms for metals and extensive experience applying them in real applications such as launch vehicles. And so that, with that said, I have Dr. Nicholas here, and we're going to together go through some of this stuff. Over to Nicholas, Dr. Nordendale.
Yeah, thank you, Dr. Goyle. Like Vinay said, my name is Nico, and I work for the Aerospace Corporation, and we're going to talk a little bit about failure criteria for metals. And so, before really diving into that, it's kind of important to go back to the fundamental ideas of stress. And so, from your mechanics class, we all learned that stress is a tensor where you have 9 directional stress components. And so, typically we can break those up pretty easily into the 3 normal stresses along the diagonal and 3 unique shear stresses. So since the stress tensor, the X, Y, and YX are symmetric, you end up with 6 unique stress values. Now that's in a 3-dimensional stress space. If you want to talk in terms of principal stresses, which you should all remember, is where you take a stress tensor and you rotate your little stress block to maximize the normal stresses. Those become the principal stresses. And those are your extreme values for any state of stress that occur when you're rotated to align with the peak stress directions. And so when we talk principal stresses, that's where you see sigma 1, 2, and 3, as opposed to sigma X, Y, and Z in the original stress tensor. We typically denote sigma 1 as max principal, sigma 2 as mid principal, and sigma 3 as min principal, where max principal is the most tensile stress, and sigma 3 min principal is the most compressive stress. That does not mean the max principal is always tensile. It could, if your overall element is in an overall state of compression, this could still be a compressive stress. It's just the least compressive or most tensile.
Very, very good. And so yeah, that's important, and we should have the experience on how to solve the cubic equation along with the eigenvectors to determine what these principal stresses are. And so so these principal stresses play a role in the failure criteria, right?
Yeah, exactly. And something we'll kind of get into in some of the later slides is that oftentimes some engineers in practice can fall into a habit of always looking at a single stress metric to try and predict failure, whether or not it's a principal stress, whether or not it's von Mises stress, whether or not it's shear stress. And ultimately, the answer isn't always straightforward. It's up to the engineer to understand the physics of the problem you're considering, what the environments are, the load types, things of that nature, to understand what the appropriate stress metric is for determining failure, which we'll show in a later slide. So, as Dr. Goyle said, there's, 2 straightforward ways that you've probably both seen before, but the common most ways to determine principal stresses. First, we've all seen using Moore's circle to calculate for what the principal stresses are. It also allows you to determine the max shear stress. Or you could, do the eigenvalue problem to set the determinant of your matrix equal to 0, solve the eigenvalues, and those eigenvalues are your principal stresses.
And in this course, we covered it using linear algebra. We covered it using the idea of the eigenvalue and the eigenvector, finding the determinant of the eigenvalue problem. And that's how we did it in this course.
Yep. Moving on to the next slide. So in terms of your state of stress, the original, 6 unique stress values over a total of 9 positions, we could also further break that out into 2 separate components of stress, which we're going to call the hydrostatic portion and the deviatoric portion, where you can think of the hydrostatic portion of the stress as the essentially, the mean stress or the average that is there to try and change the volume of an element, as opposed to the deviatoric stress, which is there to change the shape of the element. So these are 2 separate portions of the stress that do different things to your solid. And so we've denoted there sigma h, or the hydrostatic stress, is literally the mean stress, or the average of the normal stresses. You don't change the shape of your little cube of stress from hydrostatic stress. You only change its volume. You could kind of envision your little cube getting volumetrically bigger or volumetrically smaller, depending on if it's a hydrostatic compression or tension. Deviatoric is more of what we tend to think of as shear, where you tend to change the internal angles of your cube. And it is the deviatoric stress that we tend to focus on in topics of failure to try and understand when will metal actually lead to failure.
And I also want to point out that this hydrostatic definition here plays a role in the volume change. So this one tells you how the shape may not change, but the volume may change, depending upon what the bulk modulus of the little cube is.
Exactly. So if we try to think about fundamentally what is causing these things, you kind of have to get down to the atomic levels. And so our deviatoric stresses, or the shear stresses, they tend to change the shape of material, typically due to a shear stress. And so when we think of metals, because metals typically have a metallic bonds and are able to share electrons, they can cause these atoms are able to slip past each other and form new bonds along an atomic plane. So if you see kind of those images there, when you have an original configuration atoms, and as you apply shear stresses, the metallic atoms can actually shift past each other. And at the macro scale, you see here is like the actual shear failure that starts to occur. You may also cause movement of dislocation of defects. So at the atomic level, not the atomic microstructure isn't always perfect. There may be small, single atomic layers that are missing from the crystal lattice. And so as you apply some amount of shear to it, that dislocation can actually move positions. And so that kind of is graphically showing you at a micro scale what is at, or I'm sorry, at the atomic scale, what is happening when you actually see shear failure.
Yeah, so that's very important.
So to shift back to kind of the macro level, in a strength of materials class or mechanics materials class, you probably have been familiar by what we talk about an elastic behavior, or where you are stressing a material within the elastic region where all deformations are reversible. You don't have any permanent deformation, and so you have some linear elastic response up until typically a proportional limit of the material. So in the curve on the left, when we're looking at a brittle stress strain response, you see in a proportional limit at A, and then you have pretty quick fracture shortly after that. You don't have a significant amount of ductility after you reach the proportional limit. However, for a ductile stress strain response, after you exceed the proportional limit and exceed the yield stress, you can typically continue to strain the material significantly. You may experience perfectly plastic deformation, which shows between points B and C, where you don't maintain any additional added stress, but you can continue to strain. You can have strain hardening, which we see from point C to D, and eventually reaching some ultimate stress point D. Depending on whether or not you're talking about true stress or engineering stress, would be looking at path E prime versus E. And at some point, you get necking, which we typically see as a coalescence of voids and eventual fracture of your material. You'll notice that in these two images, we focus on the phrase response. It's a brittle response versus a ductile response. And that's important because it's often that students and even some practicing engineers get lulled into a sense that all metals are ductile, and that is not technically true. And we'll get into that on a later slide, that metals can behave ductile, metals can behave brittle. It depends on a number of things, including its environments and its loading type.
And
Similarly,
typically,
you could, okay.
sorry, Dr. Nordendale, I wanted to say that typically brittle failure is considered to be about 3%, and ductile failure is greater than 3%. Some literature can go up to even 5%, but I'll prefer the 3% definition.
Yeah, that I'm assuming you're talking about 3% strain.
Correct, 3% strain. I apologize.
Okay. Yeah. So, all right. So let's go to the next slide. All right. So, kind of to summarize, or I guess to continue on, you have elastic behavior, which is typically going to end in one of two ways, as we saw on the previous slide. You could have fracture in the case of brittle behavior, or if you have a ductile behavior, you may have yield and then plastic deformation or inelastic deformation. Typically, a brittle response is going to occur when the local cohesive strength between atoms is exceeded. So this could be at a material flaw, imperfection, or generally in the bulk of material. This is common in certain types of materials like ceramics, things that have covalent bonds where you don't have a sharing of electrons across all atoms. It could happen in certain polymers and even certain metals that have more of a brittle response at room temperature. Things like cast iron tends to have less ductility and more brittle behavior. Because brittle materials fail due to some inherent flaws, and those flaws can be randomly distributed, there's a lot of scatter, material scatter in terms of how those will fail. So you could take 2 or more samples of the exact same material, and a brittle failure may have a significant standard deviation in its ultimate strength. By contrast, a ductile response is typically going to occur when you have a shear stress that exceeds a critical value, particularly in a certain plane, and you have some yielding that will continue to occur. So yielding, again, is going to apply some permanent strain or deformation that's going to occur where the atoms in the material have formed some new bonds, typically, again, in metals, and they're going to have some new equilibrium position. So this is the most common mechanism is going to be slip along some atomic plane, as we saw in several slides ago. And this is most common in crystalline or polycrystalline materials, i.e. metals. But many materials can respond in either a brittle or a ductile manner, again, depending on a variety of conditions.
Yeah, very good. So, yeah, so it just depends upon whether the material responds in either brittle or ductile manner. Is that correct? So it just depends.
Yeah, and even when I, look through, actual, material metals, looking at launch vehicles and spacecraft, and we're trying to assess, failure. It's not enough to just look at, what type of material am I looking at? Am I looking at aluminum 6061 or Inconel 625? It's not enough to only look at the material type. It is important to look at the operating conditions. And so,
and on this slide, all we're trying to say, and I'll just simplify it so we can move to the next one, but is that brittle responses generally result when failure is limited by tensile strength. So it's really driven by tensile, while ductile is generally driven by shear strength. And then on the ductile one, you can see a necking response typically. While on a brittle one, you may not even see a necking response. You see more of a failure that's cleaner, not cleaner necessarily, but basically there's no change in cross section of the sample. So in brittle responses, the strength is really sensitive to flaws, and the compression strength can be greater than tensile strength. Did I get it right?
Yep, that's exactly right. And it's important to those bolded words that you kind of highlighted, that ductile response limited by shear and brittle responses limited by tension. Those are important because at some point you're going to have to decide whether or not the material that you're looking at is operating in a ductile or brittle manner, because that may change the stress metric that you use to determine or predict failure. So here, I was just going to say, I kind of been saying it a few times, but whether a material is going to behave in a brittle or ductile manner typically depends on, first, the material properties tend to be, based on the interatomic bonding or molecular structure. Like we were saying, brittle materials may have covalent bonds. They may have very low service temperatures. They may have very high rate of loading. You may have a very high degree of triaxial stress, specifically triaxial tension. And so the plot on the bottom left, the way you kind of read that is just the dotted line is looking at a fracture stress and the solid line is a yield stress. And what you see is that if you pick a point on what would be the x-axis or the horizontal axis there, and you're looking in the brittle range, as you increase stress, in those ranges, you have some high triaxiality, high strain rate, and or low temperature. And in those cases, typically your fracture stress is lower than your yield stress, meaning you will fail due to fracture or brittle failure before you will yield. By contrast, as you move to the right in that plot on the x-axis, you decrease triaxial tension or you increase triaxial compression. You may slow down your strain rate or you might increase temperature. Kind of think about metals as almost being like a silly putty kind of thing. As they heat up, they stretch a lot more, they can strain a lot more and show a lot more ductility, in which case the yield stress will drop significantly below the fracture stress, meaning you will yield before you fracture. The plot on the right is kind of showing a similar trend, but instead of looking at stress as the applied load, we're looking at fracture energy, where your fracture energy is very low for brittle responses or high triaxial tension, high strain rate, and low temperature. And as you increase triaxial compression, slow down your loading rate, and increase temperature, your response becomes much more ductile. But as this plot kind of shows, it's a pretty rapid transition, and it's depending on the material. So you have to be very aware of the material that you're using and how it behaves in the operational environments that you plan on designing it for.
So that's huge. That's huge because it's telling us that whether a material behaves brittle or ductile can also depend on the stress states and how quickly you
Exactly.
load something up. So
Exactly.
that's huge. That's huge because you can think that a particular metal behaves very ductile based on a uniaxial test, but perhaps it could behave quite brittle when you have a more complicated state of stress, right?
Exactly. Yeah, that's a really important point that engineers have experienced in design a lot, but sometimes it's not really understood in the initial design space. So this slide kind of talks about what happens when you have a material that's typically ductile. When could it behave brittle? One of the most common ways is temperature. So if you have a very low temperature, we're talking cryogenic temperatures, liquid hydrogen, liquid nitrogen, liquid oxygen, those very cold temperatures, they can be susceptible to brittle fracture. So essentially, when those very low transition temperatures occur, typically the energy of your atomic bonds has dropped to such a way that shear failure is no longer enabled. Basically, the material can't shear in the same way, and you basically overload the atomic bond in tension. So you have a metallic material that all of a sudden you drop its temperature enough, then you can cause it to fracture in a brittle way. Similarly, triaxial stress, this was one that was really elusive to me when I started practicing engineering, and it took a little bit of kind of a thought experiment to kind of wrap my head around it. But think of triaxiality in terms of tension. If you could envision a case where you have your little block of material and try and pull it in tension in all three directions, if you can actually equally apply tension in all three directions, you're not actually allowing the atomic planes to slip past each other. And so it will actually fail due to an overloading of the atomic bonds, which is a brittle response. By comparison, triaxial compression is kind of the opposite, where you are kind of compressing all the elements towards each other. But again, if it's equally triaxial in all dimensions, you're still not allowing any slippage to occur. And so you won't actually see ductility in triaxial compression as well. It's just a different failure mode. So these are two responses that can very much change, or two environments that can very much change how your typically ductile metal, like aluminum or Inconel or steel, may behave very brittle if it experiences these operating conditions. Conversely, okay, so you could also have a typically brittle material that actually behaves ductile. And here's an example of my own research where if you load a material in a very high rate, but also apply an extremely high triaxial stress, particularly triaxial compression, a highly brittle ceramic uh, actually increased its ductility. So this was a case of ultra high strength concrete that when it's confined a significant amount and you load it in compression, its ductility went up significantly. We're looking at like 14%. You never see 14% strain on concrete or ceramics under normal conditions, but put a super high rate on it that causes a typical triaxial response, you got increased ductility. Next slide. And so if you think back to your mechanics days, you probably learned about something called von Mises stress, which is a scalar quantity of stress that's a measurement of the distortional strain energy at a given point. And so if you look at the principal stresses, that's the general equation for what the von Mises stress is. And we've also given the equation in terms of directional stresses. But if you think of a 3D stress space, as shown on the right, the von Mises yield surface is the cylinder where the center line of that cylinder is the hydrostatic axis where the principal stresses are equal. So basically what von Mises says is that if all principal stresses are equal, if you are loading equally in all directions, you will not yield, which as we talked about is technically true. But essentially, as you deviate from that hydrostatic axis, that is when you start to get, you kind of accumulate von Mises stress. And eventually, the von Mises yield criterion says that at some peak von Mises stress, that is when you will yield. And so, let's see, go ahead and go to the next slide. And so, as we said, this is a very simple relationship that most analysts use quite frequently. But again, it's just a derivation of the distortional strain energy of a 3D state of stress. And so when you think back to your uniaxial tension test, sigma 1 is just the yield stress. So you pull it in tension until the thing yields. You assume in that particular case it's uniaxial tension. There, sigma 2 and 3 is 0. And so if you plug that into the equation above, then sigma 1 just is your yield stress. Now this criteria is typically pretty valid for materials when they have the same yield strength in both tension and compression, i.e. You think of an isotropic material. Typically in engineering design, most of us analysts typically will assume that the yield strength is the same in tension and compression for conservatism. We'll just use the lower of the two, which is typically for tension. That may not be physically accurate based on test data, but it may be conservative. So if your purpose is using this for design, then it may protect you for that. If your purpose is analysis for prediction, that may not be as accurate as you need it to be.
Also for weight savings could be useful, right?
Yes, definitely. If you are assuming your compressive strength is lower than it is, and your part is previously or is predominantly loaded in compression, then you probably want to take advantage of the actual material strength, not just a conservative assumption. So here just shows some test data that goes way back, kind of showing in a 2D stress space, basically the normalized stresses at yield. And what you're showing is, the solid line is the von Mises ellipse kind of taken as a slice in the sigma 1, sigma 2 plane. The dotted line, that's a trapezoid inside of the ellipse, that's your Tresca failure criterion, or your max shear stress criteria. And then of course your max normal stress is the dotted line that turns it into a square. And so you can kind of see in the sigma 1, sigma 2 quadrant 1 plane, some of the little triangles and circles and dots lie pretty close to the ellipse, some of them lie inside. And it really depends on, a lot of them are the triangles. And those triangles you see are gray cast iron. So that is showing you that gray cast iron typically fails before von Mises stress predicts you would fail. And so if you're dealing with cast iron, you really need that. Now that's not typically an aerospace material, but if you are dealing with, marine applications, or certain ground systems, you may come into contact with that type of material. And so it's important to understand test data needs to drive how you do design. And so to try and understand whether or not von Mises as a yield criterion is accurate, you really need to understand the material system you're talking about, whether or not the strength of your material is the same in tension versus compression. Additionally, one detail that I have seen a lot in industry kind of overlook is that von Mises is just that. It is a yield criterion. It is not an ultimate failure criterion. So, a question kind of came up, is it appropriate to calculate an ultimate strength margin based on a metric that is used to predict yield? So, what test data is there out there for the material you're analyzing that says that ultimate failure of this material occurs on a von Mises ellipse or on a von Mises cylinder, depending on the plane you're in? That's not to say that it can't be. You just really need to understand the materials that you're dealing with and whether or not they fail in an ultimate manner in a shape that is predictive by von Mises. So this is probably invalid when, one, material is not homogeneous in both stiffness and strength, when materials exhibit brittle response. Brittle responses typically have tension fail at a lower level than compression. And so old-fashioned yield criteria or ultimate failure criteria that have been used for a long time is known as the Drucker-Prager yield surface, which is shown as a cone in the 3D stress space instead of a cylinder. And in that case, you can kind of see when you get into triaxial compression, the cone starts to get a lot larger, right? But when you get into triaxial tension, our cone starts to contract, which would be more indicative of triaxial tension failure, which is a little bit more realistic. This is a failure criteria that's widely used in geologic materials and civil engineering, but it has been successfully used in certain aerospace materials. There's actually papers on certain alloys of aluminum, like 2014, that show a pretty significant difference in tension capability versus compression capability. And in those cases, Drucker-Prager was actually a more accurate failure criteria than von Mises was. And so this kind of just shows what the relationship is for the Drucker-Prager yield criteria. Unlike von Mises, it is dependent upon the hydrostatic stress. It can be more accurate, specifically in metals where the tension yield and the compression yield are not the same. If your material, like cast iron, has a tension yield that's like 30% or less of the compression yield, the Drucker-Prager criterion can suggest infinite biaxial compression, which is also not accurate. So these, von Mises and Drucker-Prager are not necessarily closed form solutions that are 100% accurate all the time. They have specific areas where they are very useful, but it's up to the engineers to understand the materials and, as I said, the operating conditions to understand if it's going to be an appropriate predictor of failure.
Right. So in other words, failure criteria there for guidance doesn't mean that's the Bible, right? And here, I want to cover a quick example. You have a cylinder under pressure and a radius of 1 inch and 0.02 inch. And you can see here that your hoop stress is 50,000, your axial stress is 25,000, and your von Mises is 43,300. And so in this example, you can see that this number, the hoop stress, exceeds the 43, is greater than 43. And so if the FTY or the yield tensile strength is 45, the FEA solver clearly will not predict failure yielding, although the maximum principal stress did. So the question is, will the material have yielded, Nico? That's the question now.
Exactly. And so when I wrote this example, I posed this question to some of my students before, and I asked the question, and the typical answer is it depends, because what material is this? What operating conditions were they? If this was Inconel at 300 degrees Fahrenheit, quasi-static, that's a pretty ductile material. And I would say that von Mises is probably an appropriate criteria. If this is cast iron at cryogenic temperatures, that's a very brittle response. And so I would say it would probably fail in a brittle manner, in which case 50 KSI exceeds 45 KSI. And so it might fail if this is a brittle response. And so it really depends. And this kind of simple example illustrates how it is up to the engineer to understand the mechanics of failure and what your models are going to predict.
And so that's driving us to a failure criteria we're going to be covering in a second here. And then in this example, you have the strength variation due to a state of stress. The yield strength was measured in tensile and compression. You can see the compression has a higher capability than in tension. The ultimate strength was measured to be at least 1.4 times greater in compression than tension. So you can see that happening here. And then here you have the example of a beam in bending, 4-point bending. And again, the yield strength was in terms of NY over I, which is the bending in a beam, and it was measured to be 1.12 times higher, greater than tension. You can see that there. The bending modulus of rupture, which is indicator ultimate strength in terms of NY over I, was at least 1.8 times greater in bending than uniaxial. So clearly the state of stress is playing a role, right, Nico?
Yes.
Yeah, so let's move to the next example here. You have a situation for torsional yield strength and you can write that in terms of the torsional loading times the radius divided by J, the polar moment of inertia, and it was measured to be 28% less than the yield strength. You can see that here. For von Mises criterion, we'll have predicted sigma y divided by square root of 3, and Tresca will have predicted sigma y divided by 2. Right, so you have different values depending upon what you use. Torsional modulus of rupture, which is indicator of ultimate strength, is in terms of this, and it was measured to be within 2% of the uniaxial tensile ultimate. And here you can see the different values plotted. You have the yield here, you have the ultimate here, and the failure happening here. So clearly you have discrepancies depending upon what the state of stress is, right, Nico?
Exactly. And that's kind of what we've kind of been hinting at the whole time, which is that stress is a tensor. It's not, just one single number, and it's not often acceptable to just simplify into a single scalar like von Mises or just look at max principle. It really depends on the loading type. A stress tensor is there to tell you a lot more than just a single number. You have to understand physically what is this little block of element doing. What is its shear? What is its tension and compression?
And so that now takes us to the failure criteria we'll be discussing before you go.
Yep. And so, one of the things that is really useful and has been really driven in the aerospace industry, been driven by test data, is that it has been shown that if you look at the amount of triaxiality in a given element or material, it can drastically change the ductility of that material. And so, before we were talking about a material becoming more or less ductile, or trading out ductility for a brittle response, the triaxial knockdown factor is a relationship of the first invariant of the stress tensors, I1, divided by von Mises stress. So I1, which is just 3 times the hydrostatic stress or the mean stress, divided by von Mises stress. And that creates just a scalar number that, if you kind of see in the plots below, are the x-axis. And so as you increase your triaxiality knockdown factor, you notice that the ductility or the elongation to failure drops significantly. And so that is analogous to you looking back at that original stress strain curve at the beginning of the slides, where originally maybe you had high ductility, you had a long elongation to failure. As you increase triaxiality, specifically triaxial tension, that drops to a much more brittle response. And there's lots of experimental data to show this behavior. So this is a compilation of a lot of test data. You see aluminums, steels. This was also done independently for coppers and other materials, and basically show a general common relationship where if I actually normalized all of these, you could see a lower bound is that black line, which is the relationship of the uh, the elongation predicted divided by the elongation to failure. So that's like epsilon divided by E is basically equal to 2 to the power of 1 minus TKD. So if you use that, the black line there for your material, and you knock down your capability using that, you can prevent yourself from failing due to this loss of ductility in design. And so this is a very helpful relationship that we've started to see a lot of contractors in the aerospace industry start to use in order to protect themselves from a brittle failure when it wasn't expected. And so
In
this
other
kind of
words,
shows
we can correct for the we can look at the stress state and correct it and more accurately predict failure, right?
exactly. And so I kind of outlined here like uh, the logic flow of what you would get. So assume you have a nonlinear stress strain curve, FTU, the elongation to failure. And so you go to your finite element solver, you get I1 or the pressure, you get von Mises stress, and you say, okay, the TKD is the max of either I1 over von Mises stress or 1. If it's less than 1, obviously you're basically saying you're in a compressive state and you don't want to give credit for compression. We're only trying to focus on tension. And so if you have a very, very small knockdown factor, you're just going to leave your stress strain curve alone. However, if you are in a state of heightened triaxial tension, you can calculate your reduced elongation to failure. So you kind of see there in the stress strain curve in the bottom, the original stress strain curve kind of shows you FTU and elongation to failure as like the far right top hand point. Once you calculate TKD and you reduce to epsilon R, that reduces your elongation to failure, and you can basically do a table lookup to find what your new adjusted ultimate strength is. As a general note, I often encourage analysts when you are trying to predict an ultimate margin, if you're predicting that your state of stress is above the yield strength, then your margin can be different depending on if you're talking in terms of stress or strain. They're the same when you're below the Young's or when you're below the yield strength. But once you're above it, now margin, which is typically a linear projection of capability, they're different. And so I typically encourage engineers, if you're predicted to be above the yield stress and you're trying to figure out margin, I encourage reporting margin, ultimate margin, in terms of both stress and strain. It gives you at least two numbers to get a better feel from where you are.
Well, thank you very much, Dr. Nardendale. I appreciate your time, and we'll continue then with our coverage of failure criteria. And so to calculate the ultimate margin, all you have to do is compare the von Mises stress with the FTU adjusted, which was adjusted in the manner that we described here. And then you can calculate the margin of safety. Since this utilizes a nonlinear material behavior, the factor of safety should be included in the finite element model of in the FEM applied load. Fatigue and fracture is very important too. I want to give a very top level view because in the second portion of this course, we discuss these things. The discussion of metallic failure modes in aerospace structures typically include fatigue, which is the development of a flaw in a previously pristine structure due to cyclic loading. You also have fracture, which is propagation of an existing flaw through a structure due to cyclic loading. Damage tolerance usually presumes an initial flaw. And so in the AIAA S110 standard, section 6.1.7, a fracture mechanics based damage tolerance analysis or test may be used as a substitute for fatigue analysis or test. Typically, for fatigue analysis, you can use a stress life method to quantify when failure occurs, or a strain life method to quantify when failure occurs, how many cycles it takes to fail. These two approaches are covered in a second portion of this course, but the bottom line is if you have repetitive loading at a particular stress, the number of cycles of failure could be finite. And typically you'll use the SN approach for high cycle fatigue and the strain life approach for low cycle fatigue, meaning high strains, typically beyond yield. The most popular method for fracture analysis is the linear elastic fracture mechanics, using the DADN delta K approach, also covered in the second portion of this course, and it uses the stress intensity factor to quantify the fatigue crack growth rate. Here you can see the stress amplitude as a function of number of cycles, and this is for steel, tempered steel at 600 degrees F. You can see here quickly how the number of cycles to failure drops as the stress increases. So I go from 400, I have almost infinite. When I go to 500, I have a finite number of cycles to failure. So this is data that's provided in a MMPDS type, which you should be very familiar now. And the curve shows the number of cycles to failure. Fatigue data has higher scatter, so the SN curve usually typically gives multiple curves on a single plot at various probabilities of failures. You can see here you have multiple plots at different probability of failures. But in the standard we're talking about right now, which is section 6.1.7.1, we want to use the nominal curve, which is the red curve. But depending upon the program, you may be requested to use the green curve. So just keep that in mind as you're doing the fatigue assessment of a sample under loading conditions repetitive. There's another method used for evaluating fatigue, and this method is useful because uh, you can have a stress spectra, and that spectra, sorry, you could have a particular loading event that's occurring here, and then other loading events occurring at lower stresses. What the miners rule is doing, which is this formula here, is trying to predict failure based upon the various load spectra you may have, because the stress that you're applying could vary as a function of time, depending upon what the launch vehicle of the aircraft is looking at. So an approximation that people use is called the minus rule. And what you do is you calculate the number of cycles to failure due to a particular stress level. Say that I have a stress level number I. You calculate the number of cycles to failure for that, and then you know the number of cycles at that stress level. So then you take that ratio and add it over all the different kind of types of stresses you may have. And you want to make sure that this value of C is at least less than one. You can apply a factor of 4 to that because of scatter and the fatigue data, and then you will have a C of 0.25 as an example. Minor's rule is typically agnostic of sequence in which loads come first, high or low stresses. So in general, cycles of low stress followed by high stress cause more fatigue damage than it will be predicted by the rule. And high stress followed by low stress may have less damage due to presence of compressive residual stresses. So I advise you to then use the approach that gives you the highest cumulative damage index in the calculations. Here's a visual examination of what's going on. You have stress amplitudes at different levels, and you may have a number of cycles N1, N2, N3, N4. So you can have number of cycles associated with this cycling of stress from 0 to sigma 1, 0 to sigma 2, for example. And then what you'll do, you'll record these number of cycles here in the numerator, and then you'll determine the number of cycles to failure in the denominator. So for sigma 1, I record N1, I put it in a denominator, and then for sigma 2, I put N2 as a denominator, and so forth. I'll add this together, and I want to make sure that the damage is less than 1, and if you apply the factor of safety or fatigue scatter factor of 4, then it will be less than 0.25. Linear elastic fracture mechanics is an approach to characterize the stress intensity factor, the stress intensity at a sharp crack tip. A crack tip is going to have infinite stress, so you have to find a way of predicting failure. A flaw typically will result in infinite stress, and so therefore you need a way of assessing that. One approach is to use the near crack tip stress field expressions. And then here's an example of that. You can see here that the stress intensity factor equals the load that you're applying, the square root pi A. A is the crack geometry, for example, and Y is a geometric factor. It depends on the geometry of the configuration you're studying. The strain energy release rate can be related to K1 through this formula K1 squared divided by E for plane stress. And for plane strain is this one. Bottom line is that you can use either K1 or G1 to predict when failure occurs because all you have to do is compare K1 to K1C, which is a material property that you can find through an STM standard, or G1 to G1C, which can also be calculated for any material. But when you have cyclic loading, you want to use something like the Paris relationship. Here, what you see is delta K. So you're cycling this stress here, which results in a cycles of K1. And this cyclic behavior in delta K can result in a crack growth rate. And so you have to basically use this formula of dAdn equals C delta K to the M. Again, that's covered in second portion of this course, but I'm kind of giving a bigger picture perspective so that you have a good idea what's going on. And so the complete log-log plot is shown, and you can see here how at a threshold below this value, there's limited crack growth happening. But when you approach the material fracture toughness, which is about here, then the crack growth accelerates. In this region, the intermediate region or region 2 is stable crack growth. And so what we want to make sure is that the flaw stays stable throughout the service life of the part, and you want to implement periodic inspections to make sure that flaw is not getting closer to K1C here, which could be a problem. The fracture toughness is a material property which describes the ability of a material to resist fracture and is one of the most important properties in the design and analysis of metallic structures. The linear elastic fracture toughness of a material is determined from the stress intensity factor K1 at which a thin crack in the material grows in an unstable manner. Fracture toughness is a material's resistance to brittle fracture when a crack is present. So you want to make sure that you understand what the fracture toughness of the material is because that material can be measured and it can tell us a lot about how the structure behaves. Similar to strength properties, E, the elongation, the yield tensile, and the ultimate tensile, this strength, the fracture toughness has a wide variation from one metal to another, and so you have to really measure it for every material. It can also vary across temperatures. You can see here how the fracture toughness changes with temperature and how it goes lower when you go colder. It's not true for all the materials. You could have a situation, for example, take Crest 301, where the modulus, FTY, and FTU all increase, but the fracture toughness decreases at lower temperatures. I have to keep in mind that fracture toughness is looking at understanding what will happen when a flaw is present. So again, the process is I apologize. The process is that you're going to calculate K1 from the given stress level and compare K1 to K1C. That's the general process you want to use. And then once you calculate that, then you calculate K1 and compare to K1C, which is a fracture toughness of material, and that will tell you whether crack will occur. That's for one cycle only. When you have multi-cycle loading, then you want to go into something like this where you have cyclic loading occurring, and so that's going to tell you a lot about what the crack growth rate is, and it's going to tell you whether the structure will survive because the crack growth will continue to increase as you cycle it, and so that's going to help you with that. The fracture analysis is typically done with the NASGRO code. There's two modules in NASGRO. I covered this in part two, and there's some tutorials about this. K1 is based on this one. This module calculates the stress intensity factor, while this module calculates the fatigue crack growth. The geometry in the modeling should be specified as nominal part dimensions, and you're going to provide thickness and width and radius and the initial flaw dimensions for the crack. Typically, you want to basically analyze it to the minimal detectable flaw sizes in the non-destructive inspection standards. NASA STD 5009 Table 1 gives you the minimum detectable flaw sizes for NDE, and you want to make sure your structure survives to those minimal flaw sizes. Another approach to size a flaw is to calculate the largest flaw you can ever have that passes the proof test, and then use that flaw to then determine whether the structure has sufficient life throughout, throughout its service life. An additional check should be performed, and I don't want to spend too much time here, but you want to calculate the plastic zone and make sure that plastic zone using these two formulas, whether it's plane stress or plane strain, you want to make sure that this plastic zone is at least 10% of the ligament radius and is much smaller than the crack length. Because if that's not the case, then linear elastic fracture mechanics does not apply. And then you have to use something more advanced like elastic plastic fracture mechanics. So just make sure that that the radius, the plastic zone ahead of the crack tip is smaller. And then you also want it to be between 60 to 70% of the yield stress. So smaller than this yield stress if you can. Um, and then to evaluate hardware, you're going to make sure that you have 4 service lives applied to the number of cycles with the initial flaw sizes I just discussed from the NASA ST 5009. And for example, you want to look at scratches, dings, dents with the flaws that you analyze to make sure that if you have those scratches, dings, and dents, that you're okay. But those dings, dents, and scratches need to be smaller than the flaw size that you analyze for. Material fatigue crack growth data has an inherent scatter, so that DADN curve I showed has scatter. So as a consequence, you need to really analyze to 4x. That's why you want to do that, because it will help you account for that scatter. And so if you cannot meet the initial flaw sizes from NSST 5009 and you have to come up with a less conservative initial flaw size, you may have to implement more advanced non-destructive evaluation techniques to be able to find those flaws and to be able to show good to 4x service lives with the flaws that are present. So, in summary, most of the metallic failures in aerospace applications can be handled by anchoring to fundamental understanding of topics like stress metrics, stress responses, anchoring analytical models, balancing analytical accuracy with computational cost and effort. And also, metallic fatigue and fracture are particularly complex failure modes with inherent scatter in results. And so that's why I use a 4x scatter factor. For high cycle fatigue, some people even use 10x. So this will be covered a lot more in part two of this course, but I want to make sure that you have a top level view. Again, predicting strength failure requires trying to understand the stress states and adjusting the triaxiality factors. Then you can also predict cycle fatigues, how many cycles for fatiguing a sample, and the minors rule when you have stress states that can vary over the service life. Then I cover fracture, which requires the Paris law relationship, DADN delta K relationship, and again, a factor of 4 applied to the number of cycles because of the scatter and the fatigue evaluations. So with that, we have covered this one. The composites failure criteria is covered in my composites course, which you can view. You have a great rest of your day. Thank you for listening.